Hello, welcome to this lesson of our study of differential equations, and this is our first lesson on it and the introductory aspect of it. Okay, so in this lesson we just go through the definitions, classifications, yes, and basically that will be it. And then in our next lesson we'll talk about solutions to a differential equation. Okay, so if you have not subscribed to my channel, kindly subscribe to my channel, like my video, add your comments in the comment section, share my video, and also, like I said, subscribe to my channel if you have not subscribed yet. Alright, let's start. So, differential equation. So what is a differential equation? Now, a differential equation is an equation which involves one or more derivatives or differentials of an unknown function. So you know how to differentiate functions. So if let's say the unknown, I have a function, let's say u, and I have an equation. Okay, so the first thing is an equation. A differential equation is an equation. So there should be an equal sign that involves one or more derivatives or differentials of an unknown function. Okay, so let's say if I have a function, say f, okay, that I have a differential of f with respect to t, then plus, let's say, f, and it's equal to, let's say, some x squared, or let's say t squared. Okay, let me use that simple one. Then this becomes a differential equation because there's a derivative of an unknown function f that we don't know. So in differential equation, what you do is, you having these, then you will use some ideas to solve for the unknown function. Okay, I hope you get this. So let's pick some example and talk about them. Now with the examples, we have first one to be this: x dy dx plus y equals 0. Now in differential equation, or in derivatives, let me put it that way, if you have dy dx, and if you say that y is a function of x, that is y of x. Y is a function of x, okay? Then always we say that y is the independent variable. Sorry, y is the dependent variable. Let me take that point again. Y is a function of x, meaning that y depends on x. So y here is a dependent variable, dependent, okay? And then the x is the independent, okay? Independent, okay? So just, you can write that, okay? So always the function that is f, or the variable that is a function of another variable, is a dependent, and the variable that we define others on is the independent. Okay, so in this case, in the first question, y here becomes the dependent, sorry, and then the x becomes the independent variable. Okay, look at the second one. We have d squared y dx squared plus k squared y equals 0. This is also an example of differential equation. Now look at the third one. We have del squared of v over del s squared plus del squared of v over the y squared. So this is coming from partial derivatives, and if you have these appearing in an equation, then we have another example of differential equation. This is a special type of differential equation. Okay, we'll talk about them when you have partial derivatives inside. This one too is also another example of the ones that has partial derivatives. Now with the question 4, or the example 4, you can see that here x is a dependent variable because we have dqx dyq. So we define x as a function of y. So in the example 4, we have x of y. So meaning x here is a dependent variable, okay, and y here is the independent in the example 4. Okay, so let's go ahead and do classification of differential equations. So how do you classify differential equations? So differential equations are classified generally by, first of all, type, second, order. Okay, so based on type, what can we talk about, or how many classifications do we have? Then based on the order, and then we have based on the degree, linearity, and then homogeneity. With the homogeneity, we'll pick this in one of our lessons to talk about it, okay, how to show that a certain differential equation is homogeneous. But in this context, I'll just use some simple example to explain the homogeneity. Okay, all right, so let's start with classification of differential equation by type. So generally, when you want to classify differential equation by type, you have the ordinary differential equation, which is the ODE. Okay, and this is very simple. Okay, in the ODE, is a differential equation in which it contains only ordinary derivatives of one or more unknown functions, that is the dependent variable, with respect to a single independent variable. So here, what we mean in the ODE is that your function should be a function of, or your variable, let's say y, should be a function of only one variable. Okay, so let's say y of x. Okay, so y is just a function of x, and so when you have the y dx plus, let's say, d squared y dx squared is equal to, let's say, 2x, and this becomes an ordinary differential equation. Okay, because we have the unknown function to be y, and it's a function of only x. Okay, now you can have a different case whereby you have two different unknowns. Okay, but they both depend on only one variable. Okay, such an example is this. It will be a system. You'll be giving us a system of it. Okay, so that you solve for both of them. So let's have a dx dt plus b dy dt. Okay, it's equals to, let's say, some constant c, and if I have d dx dt plus some e dy dt equals f, you will see that this is an ordinary derivative, or sorry, an ordinary differential equation, because both x and y, they depend on only t. Okay, although we have different derivatives or different unknown functions here, which is the x and the y in their derivative form, but yes, still this is an ordinary differential equation because both x and y depends on only t. Okay, now in the case where we have a partial differential equation, it's when you have the partial differential equation is one involving a partial derivative of one or more unknown function or dependent variables with respect to one or more of their independent variables. Okay, so let me give an example of this. Example is del squared v. Okay, del squared v over del s squared plus del squared v over del y squared is equal to 0. This shows that in this equation, this shows that v is a function of both x and y. So before you can get a partial derivative, then your function should be or your variable should be a function of more than one variable. Okay, or you can also as well have something like del squared u del s squared plus, let's say, del squared v del y squared plus, let's say, del u del x plus del v del x equals something, let's say, 0. This means that we have two different independent variables, u and v, and their partial derivatives. Okay, so since we have partial derivatives, then this becomes a partial differential equation. Here, u is a function of both x and y, and v is also a function of both x and y. Okay, so by type, you have two: ordinary differential equation and partial differential equation. And like I said, the ordinary differential equation consists of differential equation in which we have derivative of an unknown function with respect to just a single variable. Okay, so it means that function depends on only one variable. Okay, let's go to other way, by order. Okay, so by order, the classification of differential equation by order. Let me define what we mean by the order of a differential equation. The order of a differential equation is the order of the highest order derivative. What this simply means is that just look through the differential equations, and the higher, let's say, the higher order differential becomes the order of the differential equation. Okay, so when you look in the first equation, okay, this one, you see we have the second derivative present. Okay, so d squared y ds squared present. And then it means that since we have the second order derivative present, that is the second derivative present, it means the order of this is second order. Okay, so this is second order. So if they ask you what is the order of a differential, just look through it and look for the highest derivative present, and that is the order. Okay, so it comes to the second one. Realize that the highest derivative here is the cube y dx cubed, and it means since that one is the highest, you have a third order. Okay, somebody would have asked why we have d squared y dx squared all to the power 3. We didn't cube it. No, we don't do that. Okay, the highest derivative here is the cube y. Then d squared y dx squared is smaller than the cube y, or in terms of derivatives, this is lower than the cube y dx cube. And so what the squared y dx squared means is simply that it simply means that if I find my second derivative, okay, with respect to x, I should just cube it, and that is all. So let's say d squared y dx squared, okay, gave us, let's say, 3x. Then come and put it here and you cube it, become 3x to the power 27x to the power 3, right? When you put it there and cube it, that is what you get. But if somebody asks, why didn't we do like you cube d squared y dx squared cube, and that would be, let's say, d seth y ds to the power 6. And if this is our second derivative giving us 3x, then the fourth one will give us what? 3. The fifth will give us 0, and the sixth will give us 0 as well. And this wouldn't be, this is equal to 0, the sixth derivative, in terms of us saying that d squared y dx squared is equal to 3s. Then when you continue to the cube one, you get 3. To the fourth, you get 0. To the fifth, you get 0. To the sixth, you get 0 as well. But if you come and put the squared squared y dx squared in place of here, and you keep it, you get 27s cubed, which is different from 0. Okay, so know when to cube it and not to cube it as well. Okay, alright, so that is our thing right now. Let's go to the other one, that is by classification by degree. So what is the degree of a differential equation? The degree of a differential equation is the power of the highest derivative term present. So you just look through your differential equation. Which term has the higher derivative term? Is the first term, that is the d cube y dx cube. So its power, what is the power of this? It's just 1. The power here is 1. So here we have a degree of what? Degree of 1, or first degree. Okay, now I come to the second equation. What is the highest derivative here? Is d squared y dx squared is bigger than dy dx. Okay, then look at what is the power of d squared y dx squared. The power is 5, so the degree here is what? 5. Just look at the highest order derivative, or the highest derivative present, then look at its power, then that is the degree. Okay, here the power of dy dx is 10, but dy dx is not the higher derivative present here. Okay, alright, let's go to the next one. Classification by linearity. A differential equation is linear if these conditions are satisfied. Now the first one is the dependent variable and all its derivatives occur only in the first degree. So it means that all the differential or derivative terms present in the differential equation, if you want it to be linear, then all the differential derivatives present in the differential equation should have a first degree, or they should have a degree of 1. And also the dependent variable, its power should be 1. I mean the degree should be 1. Now the second point is no product of the dependent variable, say y, and any of its derivatives. So it means that there shouldn't be something like y prime. Y prime is the same as dy dx. Okay, or let's say y squared y prime. There shouldn't be something like that. There shouldn't be any product of the dependent variable and its derivatives. Okay, there shouldn't be like any of these terms present if you want it to be linear. Then it means that if it is something like that is present, then it becomes non-linear. Okay, so it means that if any of these is violated, then you have a non-linear differential equation. Now the last one is no transcendental function, the trig, the logarithmic function, the exponential function of the dependent variable and its derivatives occur. So there's nothing like len y, okay, or len of xy, because y here is the dependent variable in our context here. So there shouldn't be anything like that, and there shouldn't be anything like len of dy dx. Okay, so you said there shouldn't be any transcendental function of the dependent variable and its derivatives. Okay, I hope you get it, so that you can also do same for the trigonometry functions and the rest. You can try and know which ones you don't want to be present. So if all these points are satisfied, then you have a linear differential equation, and if any of these is violated, then we have a non-linear differential equation. I hope this is cool. Now let's go to the homogeneity. With the homogeneity, or let me pick examples. Okay, so the linear, with this, first of all, you check if the power or the degree of the different derivatives present is not 1. The degree here is 1. Okay, the degree of this y is also 1. So with the first point, we are okay. Now we go to the second point, which says that there shouldn't be any product of the dependent variable y and any of its derivatives. When you look through this, there is no product of such term or such term here, and there shouldn't be any transcendental function of the dependent variable y or its derivatives, and indeed nothing of such thing is here. So it means this is linear. Now come to the second one, the y prime prime. The derivatives are y prime prime and y prime. Okay, and they don't have any power. It means that their degrees are both 1. And y here is also just to the power 1, so its degree is also 1. So the first point is okay. And come to the second point, which says that we shouldn't have anything like y prime prime or y prime. There shouldn't be any y multiplying its derivatives, and indeed in this equation, in the second one, this one, there's no such thing there. Now you go to the last one, which says that there shouldn't be any transcendental function of the dependent variable. Although len x is a transcendental function, but x is not the dependent variable, so we don't care. E to the x2 is the same thing, we don't care, and cos x is also the same, but we don't care. Since we don't have any of these in terms of y, we have a linear differential equation. Now I come to the non-linear. Here, although this is of the degree 1, but y is not of a degree 1. Okay, so we have y squared, which means y has a degree of 2 here, and this violates the first point, so this becomes non-linear. Now with the last one, this one for the non-linear part, for the first term you have 4y prime prime. So there's a product of y and y prime prime, which is saying that if you want a linear differential equation, there shouldn't be anything like this. So this means that this is non-linear, even with the cos y. The cos y, cos is a transcendental function, and then if you have a transcendental function of the dependent variable, then it means what? Non-linear, and then indeed y is a dependent variable here. Now I come to the homogeneity. Okay, so let me pick an example of the general second order ODE. It's been written as p d squared y ds squared plus q dy ds plus ry plus phi of x equals 0. So this is homogeneous when phi of x is equal to 0. Then it means that the whole equation turns out to be like this. So an example is like 2d squared, or let me use the y prime prime and the rest. So 2y prime prime plus y equals 0. So this is a homogeneous differential equation, or say 2y prime minus y is equal to 0. Okay, but if I have something like y prime prime plus 1 is equal to 0, okay, then it means that my phi of x this time will be just 1, because we don't have any y in this. So it means since this 1 is not equal to 0, this equation becomes a non-homogeneous. Okay, but let me define it here. This is non-homogeneous if phi of x is not equal to 0, then it means we have the general one back. Okay, now let me pick a trial for you. There's a trial here, so classify the ODE below this one by order, degree, linearity, and homogeneity. So after you classify them, just point your answer in the comment section. Tell me if you're able to do it, and like I said, just comment. Okay, just write the answers there, and I'll mark it for you. Okay, thank you, and don't forget to subscribe to my channel. See you next time.